Hello students, welcome to Educate. Today we are going to continue with chapter number 8 of physics of class 11th. So in previous lecture we have studied about equation of continuity and different type of flow like laminar flow or streamlined flow and turbulent flow. Today we will start Bernoulli's theorem. Bernoulli theorem is based on energy conservation principle. So we can imagine a tube like this. Here suppose area of cross section is A1. Here suppose area of cross section is A2. Liquid enters with velocity V1 here. With velocity V2 it comes out, and its height from ground level is say here h1, and at this point say it is h2. Now pressure at this point is say P1 and pressure at this point is say P2. Now due to pressure difference P1 minus P2 is greater than 0. So due to pressure difference, liquid will move and some work will be done, and that work done will be change in energy. Since Bernoulli theorem is based on principle of energy conservation, so definitely we will apply that concept that work done must be equal to change in energy, and we will derive a relation in which all three types of energies will be involved, that is kinetic energy, potential energy and pressure energy. Let's see how. So for this purpose let's have a look. Consider a fluid moving in a pipe of varying cross-sectional area. As I told you, at the two corners the areas are different. Let the pipe be at varying heights, also the heights differ. We now suppose that an incompressible fluid is flowing through the pipe in a steady flow. Keep in mind, Bernoulli theorem is valid for steady flow or laminar flow. For turbulent flow it is not valid. Its velocity must change as a consequence of equation of continuity. If you remember, equation of continuity states that if there is a pipe of varying cross section, suppose here there is constriction, so at this point it is A1 V1, at this point A2 V2. Since A1 is greater than A2, so V1 will be less than V2. So that concept will apply over here also. Now a force is required to produce this acceleration. Since liquid is flowing, it means there must be a force, and that force will be created by pressure difference, so which is caused by the fluid surrounding it. The pressure must be different in two different regions. Bernoulli's equation is general expression for expression that relates the pressure difference between 2 points. Here first point, suppose this is A and B, so there must be pressure difference as we have seen, and between 2 points in the pipe, to both velocity changes, kinetic energy will change, and potential energy is based on height, that will also change. And the Swiss physicist Daniel Bernoulli developed this relationship in 1738. Up to here I think thing is clear. Now the picture we will see after it. Consider the flow at the two regions, region 1 BC and region 2 DE. Here if you see this diagram, so it will be clear. So this region, but keep in mind time interval must be taken same, and if you remember what was the purpose last time, so here purpose is area into velocity into time will give volume. And same volume here we have to consider in portion dE, area into velocity into time. Time will remain same. Velocity may differ because of area of cross section, which is different at these 2 points, right? And height as shown here, this is H1, this is H2. So if pressure difference means here pressure is higher than this point, only then liquid will flow. So let's see in the back. So net is a little slow, so don't worry. Now consider the flow at 2 regions, one BC and 2 DE. Consider the fluid initially lying between B and D in an infinitesimal time interval delta t. This fluid would have moved. Suppose V1 is the speed at B and V2 at the D. Then fluid initially at B moved a distance V1 delta t, and V1 delta t is small enough to assume constant cross section along BC. So you can understand it this way. Here this portion, small portion, here B and C. So we assume that time taken is delta t, which is small, and here velocity is V1. So we can find this is area, so we can get easily volume. Volume will be area into velocity into time, because velocity means distance upon time, time will cancel out. So same concept we are applying here. So it says, then fluid this thing. Now in the same interval delta t, the fluid initially at D moves to E. The same picture we can see at right corner, there also it moves certain distance. Now a distance equal to V2 delta t. Pressures P1 and P2 act as shown on the planes faces of the areas A1 and A2 binding the 2 regions. The work done on the fluid at left end will be equal to, what is work done? What is rule? Work equal to force into displacement. So pressure into area will give force. So at the left end pressure is P1, area is A1. So this is force times displacement, velocity into time. So that is equal to, we can write P1 into delta V. Is it okay? I think you've understood area, and from here we will get distance, that is why delta V. Since the same volume delta V passes through both the regions, from the equation of continuity, the work done by the fluid at the other end, second end, it will be same thing, P2 A2. At that corner pressure is P2, area of cross section is A2, and at that point velocity is V2 and time is delta V. So we will get P2 delta V. Right? Up to here I think thing is clear. Now so work done on the fluid is, here we are considering right corner, means suppose this like this. So here at this corner, what is work done? So that will be minus P2V. So the total work done on the fluid, here W1, here W2. So we find the difference. So P1 minus P2 times delta V. Right? Part of this work goes into changing the kinetic energy of the fluid, and part goes into changing the gravitational potential. So this work done will cause to change in energy. Some part goes to change in kinetic energy, another part goes to change in potential energy. If the density of the fluid is rho, then mass can be written as volume into density. A1 V1 delta T will give volume, and you are multiplying by density. So delta V times rho is the mass passing through the pipe in delta T. Then change in gravitational potential energy, mgh. So height at the two corners, here it is h1, here it is h2. So mgh2 minus mgh1, and you have seen that m can be found by this formula. So m here, rho delta V is mg and h2 minus h1. So this is change in potential energy. Now, change in kinetic energy, mass is same, half mv square, and here mass, as you have seen, mass can be written like this, rho times delta V, and velocities are changing. Here velocity is v2 at this corner, and here velocity is v1. So this will be changing in kinetic in delta k equal to this. Now, it's obvious this work done will cause change in potential energy, this, and change in kinetic energy. So you can equate the two equations. If you equate, so you can write this P1 minus P2 delta V equal to change in kinetic energy this much, 1 by 2 delta rho delta V, V2 square minus V1 square, and change in potential energy this rho G delta V H2 minus H1. So we write these values here. Now what you do, take all negative term. Here minus P2 delta V, you can shift to RHS. Here 1 by 2 rho delta V and minus V1 square. So that term you can take to LHS. And similarly here rho G delta V H1 you can take to LHS. So all terms containing script 1 will come in LHS, and all terms containing script 2 will go to RHS. So you will get this is same thing, divided by delta V is cancelled first. So we will be left with P2 minus P1 and equal to 1 by 2 rho V2 square minus V1 square plus rho G H2 minus H1. Then do that I said. So you will get P1 1 by 2 rho V1 square plus rho GH1 plus equal to P2 plus 1 by 2 rho V2 square plus rho GH2. So this equation is called Bernoulli's equation. Right? So since there is script only changing 1, 1, 1, 2, 2, 2, so we can say that in general it will be equal to P plus half rho V square plus rho GH equal to constant. So this is Bernoulli's theorem. I think you have understood. I am giving you a quick recap. So this is tube. Here suppose area, here velocity is V1, here velocity is V2, and at this corner area of cross section A1, this corner area of cross section A2, height is H1, here height is H2. So first of all we find work done. So work done will be equal to pressure difference P1 minus P2 into pressure difference into delta V, right? Then change in kinetic energy half, and in terms of density we can write as you have seen. So Ke, change in Ke we find, so that will be equal to half this much, half rho times delta V, and here delta V should, the term should come over there, 1 by 2 rho times delta V V2 square minus V1 square. Similarly we find delta U, change in potential energy. So height difference is there, so we write mass like rho G delta V H2 minus H1. Now we equate work done must be equal to change in energies. So we get this relation, right? So Bernoulli equation is one very important equation, and it is based on energy conservation. Here one important point, if suppose flow is horizontal, in that case H1 and H2 will be same. So these two terms will vanish. In that case we will get P1 plus half rho V1 square equal to P2 plus half rho V2 square. So there will be such questions, and we will solve them by using this concept. Let's read it further. Here some more information is given. In words, the Bernoulli's relation may be stated as follows. As we move along a streamline, the sum of the pressure, the kinetic energy per unit volume, and the potential energy per unit volume rho G remains constant. Note that in applying the energy conservation principle, there is an assumption that no energy is lost due to friction. Keep in mind, If there would be friction, in that case, definitely this theorem will not hold. But in fact, when fluids flow, some energy does get lost due to the internal friction. This arises due to the fact that in a fluid flow, the different layers of the fluid flow with the different velocities, these layers exert frictional forces on each other, resulting in a loss of energy. This property of the fluid is called viscosity. So now we are going to study viscosity and we discuss in more detail in later section. The lost kinetic energy of the fluid gets converted into heat energy. Thus, Bernoulli's equation ideally applies to the fluid with zero viscosity. Keep in mind, this thing is important. Non-viscous fluid, there should not be any viscosity. Another restriction on application of Bernoulli theorem is that the fluids must be incompressible, as the elastic energy of the fluid is also not taken into consideration. If it will be compressed, in that case, certain energy will be lost in that case also. In practice, it has a large number of useful applications and can help explain a wide variety of phenomena. For low viscosity incompressible fluids, Bernoulli's equation also does not hold for non-steady or turbulent flow. So question may come whether Bernoulli theorem holds good for turbulent flow. Your answer should be no, because in that case situation, velocity and pressure are constantly fluctuating in time. When a fluid is at rest, if there is no velocity, then what would happen? The velocity term here, these two terms will cancel out. So we will get P1 plus rho GH1 equal to P2 plus rho GH2, or P1 minus P2 equal to rho GH2 minus H1. So this is all about Bernoulli's theorem. Thank you for watching. Team Educate.